Okay, cool. It's recording.
Awesome.
Okay, so we have here Ben. He's going to make an announcement and then give us a beautiful talk. So go for it, Ben.
A lot of pressure, beautiful talk.
Mm-hmm.
Yeah, so this is, I think, mostly a reminder to everyone because everyone received this information in some capacity, but you have to advertise as much as possible. So this weekend, virtually, there's going to be East Coast Operator Algebra Symposium 2020 at the University of Virginia. So this is a photo of what everybody who's not physically going to be here is missing. So you can scroll down, you can see the program description. We have some speakers who've already given us their titles and abstracts and stuff. The important thing is if you want to attend, you have to register. And so to register, you just click on this link and it'll take you to something where you enter your information. So this is my way of preventing Zoom bombing. And that way you're not put in a waiting room or something. I don't have to let you in. You'll receive an email with a Zoom link and you just click that email and then you should be able to join. So I don't know, take a look at the website sometime. If it seems interesting to you, please show up. It should be fun. All right. So I'm now going to do a different share. Okay. So yeah, this is a talk about a random matrix approach to the Peterson-Thom conjecture. And so I'm going to start by, I guess, because the audience is now a little eclectic, this is not quite a recall. So what I'm going to recall the following. So given a countable group G, and a vector psi in L2 of G, I'm going to let script L of G, well, I guess I don't need this. So I'm going to let script L of G be the set of vectors in L2 of G so that psi convolved with eta lands back in L2 of G for every L2 vector G. So here, right, the convolution, well, it defines just by the Cauchy-Schwarz inequality a well-defined function on G. And I say, look at the ones which send L2 vectors on G back to G. And it's a cute exercise using the closed graph theorem. So by the closed graph theorem, I have a bounded operator. So the fact that it's everywhere defined is true by assumption, basically. But I have a bounded operator just given by convolving. So the closed graph theorem tells you that that's actually bounded. And so I'm going to let LG be the set of these bounded convolution operators. And this is called the group von Neumann algebra. So you can check that this is indeed a subalgebra. Sorry, subalgebra B of L2 of G. And it's closed under adjoints. And it's closed in, say, the strong operator topology. So I won't define what the topology is. Properly speaking, I mean, what I'm about to say is not a precise definition of it, but you can just think of it as saying that if I have a sequence, so if I have a sequence of bounded operators, then it converges to another in the strong operator topology if Tn psi minus T psi goes to 0 in norm. Okay, properly speaking, in order to properly describe the topology, I should really use nets instead of sequences because this topology is not metrizable. Okay, you can basically restrict to bounded sets where it is, and so let's sort of largely ignore this. I don't want to properly define the strong operator topology, but this is largely how you should think about it, right? This is an analysis seminar, so we think about topologies in terms of convergence. Okay, so this is a case of a more general definition. The group von Neumann algebra above, a von Neumann algebra in some Hilbert space is a star subalgebra. So that just means that it's closed under products, sums, scaling by complex scalars, and the adjoint. I require that the so von Neumann algebra M in B of H. I require that the identity operator is an M, and M should be SOT closed. If you require H to be separable, that's I believe equivalent to saying that M is closed under SOT limits of sequences, but in general, just in the topological sense, which I'm sort of waving my hands around. Okay. Now there's one. I'm sorry that a lot of this talk is going to be hammering you with definitions. There's one really, really important case of von Neumann algebras, which are what are called the hyperfinite ones. So to say that a von Neumann algebra is hyperfinite, there should be an increasing chain of finite dimensional von Neumann algebras so that M is the closure of their union in the strong operator topology. So the classical example, and again, I'm going to be sort of vague and not super precise here, is you can take some sort of infinite tensor product of the 2x2 matrices. Properly speaking, what I'm saying here is there's some way to include the 2 to the n matrices, 2 to the n by 2 to the n matrices, and the 2 to the n plus 1 by 2 to the n plus 1 matrices by just embedding them block diagonal. And there's some way to take a limit of these objects and end up with something hyperfinite. Okay. Now, I don't actually need this for my main result, but you kind of have to mention it now. So the sort of Fields Medal winning work of Alan Kahn in 1976, gives various other, which I won't write down, gives various other criterion to be hyperfinite. I guess it's maybe not entirely clear, but right, somehow a hyperfinite feels like a very strong condition. You're saying that it can be approximated by the finite dimensional situation in a very nice, almost sort of uniform way. That's maybe something that's hard to check. This work of Alan Kahn, reduces to checking to much, much easier conditions. Okay, so let me start right away. Is there a question? I thought I heard something. Okay, let me start right away by mentioning what the Peterson-Thom conjecture is. And then I'll explain where it comes from and sort of why you should care. So the conjecture says the following. If you take a subalgebra of the group von Neumann algebra corresponding to the free group, FR here is the free group on our letters A1 to AR. That is hyperfinite and diffuse. So I haven't defined diffuse, but think of this as an analog, as a non-commutative analog of L infinity on the unit interval. What it means, properly speaking, is that if you have a projection in this von Neumann algebra, and just from general theory, von Neumann algebras have like tons and tons and tons and tons of projections. If you have a non-zero projection in this von Neumann algebra, there's another non-zero projection, which is under it, but not equal to it. So under it here means, projections correspond to closed subspaces, and that closed subspace should be contained in, if Q is under P, it means that the image of Q is a subspace of the image of P. Okay. So this is hyperfinite and diffuse. Then there is a unique subalgebra P in between N and LFR, which satisfies the following conditions. One, P should be hyperfinite. P should be, it should be maximal hyperfinite, sometimes called maximal amenable because of this work of Kahn that I referenced. So if I have a subalgebra which is between P and LFR, and Q is hyperfinite, and Q equals P. And finally, oh no, that's it. Yeah. So there's a unique P which satisfies this. I guess I should mention a few things here, particularly because there's some people who aren't experts in von Neumann algebra theory in the audience. So a few comments. This is maybe the most obvious one I should have made earlier, like in that it's more obvious that I should have made this earlier. First of all, this is not hyperfinite for R bigger than 1, and that corresponds to the fact that free group free groups themselves aren't amenable. Again, I haven't defined amenable, but if you know what amenable means, then the first example you see of something non-amenable is F2. So, okay. So that's not hyperfinite. I should mention something about these two conditions here. The fact that any hyperfinite is contained in a maximal hyperfinite is just Zorn's lemma. I say just here, but there's a lemma hiding in the background, which is that the closure of an increasing union of hyperfinite subalgebras is hyperfinite. But yeah, okay, that's true. So the statement here about the Peterson-Thom conjecture is really about the uniqueness. Like a priori, you have some hyperfinite thing here, and you have LFR here. And when you look at the maximal hyperfinites above P, like a priori, there are tons of them, right? But Peterson-Thom says that doesn't happen. Now, before I get to the motivation, I want to mention one other reformulation. Again, I apologize. Fortunately, this is going to be a lot of this talk is throwing definitions at the board. And the reformulation is in terms of what's called the absorbing amenability property. So we say that N inside LFR has the absorbing amenability property if whenever Q is inside of LFR is diffuse, amenable, so hyperfinite by Kahn, and Q intersect N is diffuse. So think of this as just saying that it has large intersection with N. If this doesn't happen, then more or less up to direct sums and other things that I don't want to get too technical. More or less, Q intersect N has to be just like a bunch of matrix algebras put together. That's not quite true, but okay. And if this is diffuse, then Q is inside of N. So it absorbs any amenable thing or equivalently hyperfinite thing that sees large pieces of it. And so this is not entirely obvious if you're not well versed in von Neumann algebra theory, but for those of you who do work in von Neumann algebras, this is just an exercise. The Peterson-Thom conjecture is equivalent to saying that if N1 and N2 inside of L of FR are amenable, well, let me say two things. So if P is maximal amenable, then P has the absorbing amenability property. And it's also equivalent to saying that if N1 and N2 inside of L of FR are amenable and they have diffuse intersection, then the von Neumann algebra they generate, so I use join for that. So that's the von Neumann algebra generated by N1 and N2 is amenable. Okay, so if you have two subalgebras with large intersection, then their join is amenable. This is typically not the case for most von Neumann algebras you look at, and the conjecture is that this is true for the free group factors. And this finally, unfortunately, 15 minutes in, brings us to our motivation. So why would you care, first of all, and why would you care about the Peterson, or why would you think the Peterson-Thom conjecture is true? And let me just say a few things about it. So why do you care? Well, I mean, I don't know. For me, we understand, it turns out we understand these hyperfinite von Neumann algebras very well. Let me not go into too much about what that means, but because of Kahn's work and a bunch of other things, we can, broadly speaking, classify them. Okay, and somehow the first example of something non-amenable you see from some world, in this case groups, is the free groups. And so, the next thing we should try to understand are the von Neumann algebras associated with free groups, and the short version of that is that we don't understand them. So to me, anything that tells you about the structure of like maximum, that gives you really good information about the structure of maximal subalgebras of anything interesting is cool. And particularly it's interesting if we can do it for the free group because, I don't know, we just don't understand the free groups very well, at least they're von Neumann algebras, right? Like there's the major open problem, which is whether or not they give us different von Neumann algebras. Like we don't know that. So that, I don't know, that makes any question about free group factors interesting to me. But also, there are group analogs of the PT conjecture. And the simplest and the one that, to be honest, doesn't have enough, content behind it is that if you take two amenable subgroups of free groups and they have infinite intersection, then the group they generate is amenable. Now for free groups themselves, this is kind of a silly statement because all amenable subgroups are just cyclic. And for two cyclic groups, it's kind of direct to tell when they have infinite intersection. One has to sort of be a power of the other. And so this doesn't have much content for it, but this is also true for groups. And this may seem like a bizarre statement, but analytically similar to free groups. The precise statement here is what's called measure equivalence. But basically what I'm getting at here is not only is this true for free groups, it's true for other things that have like geometric or measure theoretic conditions that are similar to free groups, like hyperbolic groups or something like this. And for those we know it, and we have a proof for analytic reasons. So there's like a proof by Peterson and Thom using what's called L2 Betti numbers. And so in general, it's pretty naive to expect that properties of groups would translate to properties of group von Neumann algebras. It's usually group von Neumann algebras are much harder. But if you have an analytic proof of what you're sort of, something involving representations or Hilbert spaces or something of the property in consideration, then you feel like you have a good shot at it. For the operator algebraists in the crowd, of course, the motivation for this whole study goes all the way back to maximal hyperfiniteness of L of Z free product 1 inside of L of F2. So this is work of Popa in 83. And which sort of started the whole study of maximal hyperfiniteness. There's a long story here that I'm not doing the best job of giving, but essentially, before Popa's work, people sort of expected that all the maximal subalgebras of things which are called factors. So anyway, don't worry about what that is, but something like the von Neumann algebras of free groups, people expected that all these maximal hyperfinite subalgebras were themselves very non-abelian, like hyper, also factors. So they had trivial center. And his work was the first to show that in fact, maximal hyperfinite subalgebras could be commutative, and that's rather surprising. He also showed that there were maximal gamma. Don't worry about what that means for now, or at all in this talk. But it's a very significant thing for those of you who know von Neumann algebras. And so, this also gave various criterion. So it gave criterion to prove maximal hyperfiniteness. Okay. And this, by work of Cyril Houdier in 2014, gave a modification of Popa's criterion, gave criterion for proving the absorbing amenability property. If something is maximal hyperfinite and has the absorbing amenability property, it's automatically the unique maximal hyperfinite extension containing anything else diffuse and hyperfinite. So, this proved it for L of Z free product 1. And there's been lots of other applications of related things. Again, I don't have time to go into details on these things, but this is me just flashing some names at the board. So these next papers by Boutier and Carderi and Boutonnet and Houdier don't use this modification of Popa's approach. They use analysis of states. So we now have lots of ways to show that things have the absorbing amenability property. But unfortunately, in order to attack the Peterson-Thom conjecture, we'd have to show that every maximal hyperfinite subalgebra of a free group factor had the absorbing amenability property, which would mean that we would either have to really nail down what the maximal hyperfinite subalgebras of free group factors are, or we'd have to come up with different techniques. Like the problem is, the techniques we have, they're beautiful, they're great, they're fantastic. But they don't, they only apply to specific examples. We need something that sort of works for every maximal hyperfinite out there. And this is where I come into the game, because there's, this was in terms of what's called this is sort of a modification. Well, these two things are, these are modify Popa. This here is doing some cool stuff with states. But there's an approach using free probability and random matrices to prove that this algebra L of Z free product 1 inside of L of F2 has the absorbing amenability property. And that's in my paper with David Jekyll, Brent Nelson, and Thomas Sinclair. Okay, so I'm going to transition to that. So here is where I'm actually going to start defining things. So we're going to leave the Peterson-Thom conjecture for a bit. I'm going to come back to it definitely by the end of the talk. But we're going to leave it for a bit. And I'm going to talk about some, a little bit of free probability and random matrices. So this next definition is going to seem kind of out of the blue, but we'll circle back in a second. So a trace of von Neumann algebra is a pair M tau. M is a von Neumann algebra, and tau from N to C is a linear functional. So it's linear in the linear algebra sense. So first of all, it should be what we call a state. So you should think of these first two conditions as an analog of being a probability measure, right? Like if M were abelian, it would turn out that once I had such a tau, which satisfies the first and the other things I'm going to write down, that this pair would really secretly be L infinity functions on some measure space with some probability measure. And that corresponds to the fact that somehow I'm saying that when you integrate, when you take tau of a non-negative thing, it's a non-negative number, and that tau of the whole space is 1. If you integrate the function 1, you get the number 1. It also should be faithful and lastly is a condition I will also not define. It's what we call normal. You would like to say this means it's SOT continuous, but that's not quite true. Anyway, don't worry too much about this. This is just a mild continuity hypothesis. Essentially, you can think of it as meaning for the uninitiated, you can think of this as meaning that I didn't use the axiom of choice to construct tau. Okay. For the group von Neumann algebra, we have a good example, which is X inner product Dirac mass at the identity, inner product Dirac mass at the identity. So if you explicitly write it as a convolution operator, that is just evaluating that vector at the identity. Right? I should sort of mention in the case G equals Z, which is in some sense very far from what we're talking about, but still good for intuition. This thing where you evaluate at 0, right? We know that that corresponds to integrating over the circle under Fourier transform. So this is okay, right? Fourier takes convolution operators to multiplication operators, and okay. All right. So if I have a tuple, and for me, these are going to be not necessarily self-adjoints. So given a tuple for some integer r, in a tracial von Neumann algebra, its non-commutative law is the linear functional L sub x defined on all non-commutative star polynomials which is just you apply the polynomial to x and then you take the trace. So this is non-commutative star polynomials. And so again, I'm not going to be super precise about what that means, but it's expressions like, right? Just as with usual polynomials, but hey, you can also just throw some stars in here if you want. Okay, and if M is closer to adjoint, so if I take this polynomial and I just replace each of the TJs with one of the XJs, I get some element in M. Okay, there's some way to make this precise using free star algebras or something. I don't want to worry about it so much. It should be, what you see is what you get. This is called a non-commutative law because it nicely lines up in probability with what's called the distribution, or sometimes the law of a random variable. So if you have a real valued, let's say complex value, so you have a C-valued random variable on some probability space, which you usually ignore because that's sort of the idea of probability, or one of the ideas. So if you have a complex valued random variable, you have its distribution, which is some probability measure, some Borel probability measure on the complex plane. And let's say x is L infinity. You usually don't assume that, but we will, just to simplify things. If it's L infinity, then just by the Stone-Weierstrass theorem, you can characterize it by saying that if you take a polynomial in Z and Z bar, and you integrate that polynomial against this measure, I guess it's just be d mu of Z, right? Then you get the expectation of that polynomial in X and X bar. Okay. So because it's compact, because this measure is compactly supported, that follows from X being L infinity, you can uniquely characterize it as the compactly supported measure, which does this equation, right? And this is sort of saying L sub X of P is, remember, trace is our version of expectation. Well, there's this difficulty that the polynomial is not commutative. Let's just ignore that. Okay. Cool. Now, we're going to denote sigma sub r to be the space of all laws. So this is the space of all laws in R tuples, where m tau is any tracial von Neumann algebra. And given a positive C, we're going to let sigma RC be the set of all laws in tracial von Neumann algebras, where I do something that appears unnatural, but let me explain that it's not actually a huge deal. I require that the operator norm of these is at most some constant C. Because it's in some von Neumann algebra, it consists of some bounded operators, and so it has some operator norm. Okay, so you can actually, for those of you who know the spectral theorem, you can recover this norm as by the following expression. So this actually is encoded into the law. So, right, sigma sub r, the space of laws, it's inside of, it's a space of linear functionals on the space of star polynomials. So it's inside the algebraic dual. Algebraic dual meaning I haven't put any topology on the underlying vector space they're defined on, and so there's no continuity restriction. But once it's a space of linear functionals, I can give it the weak star topology. And so this turns this sigma sub RC into a compact space. And now we're really happy, right? The easiest way to make a functional analyst happy is to hand him a compact convex set and some weak star topology, right? Then you're having a very good time, right? Then you're exactly where you want to be. So okay, now we're exactly where we want to be. Okay. Now, what the heck does this have to do with von Neumann algebras, other than it somehow is like a, parameterization space for von Neumann algebras? I mean, I said something about random matrices and free probability. This falls into free probability. I haven't said anything about matrices yet. So I'm going to use these space of laws to define a way to approximate von Neumann algebras. So given a tuple in some tracial von Neumann algebra, a weak star neighborhood of the law of X. So weak star weak star neighborhood of the law of X inside the space of laws in an integer n. We define Voiculescu's microstates space to be, I guess this is a bad way to do it. So this is gamma n O. This is the set of all R tuples of n by n matrices whose law is no. And then for technical reasons, basically in operator algebras, you can't do anything unless in functional analysis in general, you can't do anything without norm bound restrictions. So you have to insert them in for technical reasons. For those of you who actually are in the know and know how Voiculescu's microstate spaces are defined, yes, this is technically not the definition. No, it doesn't really matter. And anyway, we're all friends here. A talk with 13 minutes left is not the best time to get into technicalities. Okay, so this is some space of approximates for your von Neumann algebra. For instance, you can say that X has microstates. This is a definition. If for every neighborhood of the law of X, there is some integer n. Equivalently, turns out for all sufficiently large integers n, so that this space of microstates is not empty. And for those of you who know, this is equivalent to saying that the von Neumann algebra generated by X satisfies the Kahn embedding problem. Okay. So we have a notion then of when a von Neumann algebra can be nicely approximated by finite dimensional ones, by matrix algebras. And again, and another thing I'm going to not define, this led Voiculescu to define what's called the free entry dimension of a tuple. And I won't say much about it other than if you look at the canonical generators for a free group, should really not use R, but anyway. Then this tuple has free entry dimension R, and this ends up being some application of random matrices. It ends up being a consequence of the fact that if I choose R independent n by n Haar unitaries, then their law converges to the law of this tuple. Okay, now the only other thing I'm going to say about this is that, first of all, it's basically always at least one. That's not always true, but it's true in the cases we care about for the purposes of this talk, and that it's not a priori an invariant, right? And this makes us sad, right? It could be, we don't know, so I'm not saying this is true. So maybe there exists XY, which have different free entry dimensions, but equal generated von Neumann algebras. That would be bad. That would be not an invariant. I'm going to be, in fact, bold here and conjecture that actually it's not an invariant, but you know, in certain circles, that's heresy. So okay, cool. And so this makes us sad, but the nice thing is that work of Ken-Li Jung, it's implicit in here. If you read his paper hard enough, you see that it's there, but explicitly due to me. There's a related thing called the one-bounded entropy. It's a modification of the free entry dimension. I didn't mention, this is bad, I didn't mention this, but the free entry dimension is sort of some sort of measurement of how many microstates you have. And sometimes it measures like how big this microstate space is. And the one-bounded entropy also does this. but it has the property that it can be computed on a set of generators. I'm not going to give you the definition because, this is, it's like, the UCT or the assembly map or something like this. It's a technical tool which does the job you want, but you don't define it in a talk. However, this is an audience of mathematicians, so I'm going to do you better, which is, I think this will make you happier. I'm going to give you some axioms. These don't characterize it, I think. They might, I don't think so. But they're enough to get the applications for the purposes of this talk. So first of all, the one bounded entropy is either is some real number between 0 and plus infinity or minus infinity. And it's minus infinity if and only if M does not have microstates. So if you have these finite dimensional approximations at all, it's always non-negative, could be infinite. It's 0 if M is diffuse and hyperfinite. So far, this would be boring because the invariant, which is 0, whenever you have microstates, satisfies this. But fortunately, there's one case where it's not 0. It's infinite if you take a free group factor with index bigger than 1. And it satisfies some weak subadditivity. So I need that if I have two subalgebras of M which have diffuse intersection, then the one bounded entropy of their join is at most the sum of these. Yeah, so I need these to be diffuse. Right, because if you don't take them to be diffuse, there's a counterexample. You could take N1 to be L of Z free product 1, N2 to be 1 free product L of Z. The von Neumann algebra they generate is the von Neumann algebra of a free group, but they have the right hand side is 0 and the left hand side is infinity. And there are others, but I'm already running against the clock, so I won't mention them. But they are very important. Now, already from the axioms I wrote above, there's a conjecture. Again, it's kind of due to me, but I talked to Jesse, and he and Kenley kind of already had this idea around. It's not a difficult observation. So we'll call this the one-bounded entropy conjecture. And it says that if so if you take a subalgebra of a free group factor, which is diffuse, I always forget, if I forget, everything in sight should be diffuse. Otherwise, it kind of becomes meaningless. So then this one bounded entropy is 0, if and only if n is hyperfinite. So we should actually characterize hyperfiniteness. That would be the conjecture. And so notice just from the axioms that I briefly erased, this never seems to properly catch everything. So. Oh, wow, this was really bad. I almost had to erase everything. So notice from the axioms above that this implies, just from subadditivity in the second axiom, this implies that every maximal hyperfinite has the absorbing amenability property, right? Because if some other hyperfinite von Neumann algebra intersects it diffusely, well then by subadditivity, their join has entropy 0, and so their join must be amenable, but then by being maximal amenable, it must be equal to what you started with. So, okay. So this is the one bounded entropy conjecture. I'm almost getting to state my theorem, which is good because we're getting to the end of the talk. So the one bounded entropy conjecture implies the Peterson-Thom conjecture. That's not hard to see. What takes a bit more work to see is something again related to random matrices, which is this notion of strong convergence. So this is going to be a new topology on the space of laws. So I mentioned this, but okay. So given a law in our tuples, you can always cook up a representation into some von Neumann algebra. Well, I guess this is true by definition, but there's a canonical way to do it so that the trace recovers the law. Okay, and so I'm going to define the L infinity with respect to L norm of some non-commutative star polynomial as the operator norm of pi L of P. And I remember I said that this was the sup over K of L of P star P to the K to the 1 over 2K, the sup over integers K non-negative. Maybe at least one. Yeah, okay. Right. So this L infinity norm, it's not continuous in the space of laws, but it's semi-continuous. And so this defines a new topology. Let me not properly define it. This is a strong topology. Let me again just say what it means to converge. So a sequence of laws converges to another strongly. This is kind of a bad name, but fortunately it's what people chose. So this is if and only if they converge weak star and the norms converge. Okay. So equivalently, you can say this by saying, if you look at a self-adjoint polynomial and you look at its spectral measure with respect to this law, reconvergence means that for all choices of self-adjoint polynomials, those spectral measures converge weak star to the spectral measure, with respect to the limit law. And this is saying that you have spectral measure convergence plus Hausdorff convergence of the spectrum as a compact set. So now I can finally get to, so I guess I should mention one thing about strong convergence. It's motivated by this really, really phenomenal work of Haagerup-Thorbjornsen in 2003, which said that, you basically have this for what you'd think it would go to for random GUE for the GUE ensemble. And then this was followed up by lots of other people. There's now lots of machinery to do this. Collins has been working a lot on this. And so now I can state the theorem. I'll say a few words about it and then I'll end. I guess I need one. Yeah, let me say it like this. So I'm going to call this the tensor HT conjecture. So if U1n, URn are R n by n independent, hard distributed unitaries in U of n. So what I mean is take n by n matrices, which are unitary. So that's a compact group. So it has a Haar measure. So take the Haar measure on that and take R copies of that. Then, and actually, I need two of these. I need two R. So I'm going to call some U and some V. Then if I look at the law of UN tensor the n by n identity matrix and the n by n identity matrix tensor Vn, then this converges to the law of lambda a comma 1 comma lambda a in the copy of the free group with itself. So here the free group is generated by A1 through AR, and lambda here just means, convolved by this group. So you just take it inside the group von Neumann algebra we defined before. So one thing I want to say before I realize I'm basically already over time, but I'm just going to say quick thing about this, state the theorem and then finish. If I were to cover up either side, like if you were to just cross out the one side here. So if I were to just remove the identity tensor V on the left-hand side and the 1 lambda A on the right-hand side, then this would just be a consequence of Haagerup-Thorbjornsen, the fact that you could just tensor with 1. Once you start adding in left and right, it becomes really unclear and still open. And indeed, there's a good reason, and this is the main theorem of the paper. This is why there is a random matrix approach. So let's consider following statements. First, the Peterson-Thom conjecture. Second, the one-bounded entropy conjecture, right? That if you take something amenable inside LOFR with one-bounded entropy 0, sorry, if you take something inside LOFR with one-bounded entropy 0, then it is amenable. And tensor HT, then the theorem says that 3 implies 2 implies 1. And remember, this I said was not hard. 2 implies 1. And so, it's not a super long proof, but there's some non-trivial things that go into it. This uses concentration of measure in sort of a clever way. It's not surprising that you use concentration of measure, but it's sort of maybe surprising how it shows up. And it relates, unfortunately, I don't have time to explain this, but it relates back to this work of myself, David Jekyll, Brent Nelson, and Thomas Sinclair. Uses similar methods. Basically, what it says is that if you have something with one-bounded entropy 0, then when I choose 2 embeddings, when I use these random matrices given by these unitaries, which it's guaranteed by Voiculescu that gives some way to model the free groups. If I use those unitaries to produce 2 different embeddings of the free group factor, then if I restrict it to something which is one-bounded entropy 0, those random embeddings are going to be unitarily equivalent. So it gives you a randomized version. If you could prove a randomized version of Young's theorem that amenable is the same as saying you have 2 different embeddings, then you would solve the Peterson-Thom conjecture. And there's been some nice work related to Kenley-Jung's theorem by Scott Atkinson and Sri Kuna. Welcome, Ilya Valley. So it relates to some interesting stuff, but I'm already over time, so I'm going to stop here.
Thank you. Thanks for the talk. Anyone has any questions? I see that Roy pointed out that your conjecture is not recorded, so it's going to go online whether you like it or not, I guess.
Is the conjecture not recorded?
No, the conjecture is recorded. The one
yeah. Well, the paper's already online. So.
Mm-hmm. Well, it was in reference to when you spoke of heresy.
Oh, right.
But now it's on record, so.
Yeah. Well, hopefully Voiculescu is not going to watch the video. I don't know. I can have an opinion. I mean, nobody knows if it's true, right? So I can have an opinion.
Okay. Are there any questions for Ben?
I have some questions, but maybe I'll ask one while it's recording and other ones later. Just if you go back, so the convergence slightly higher, the point is that convergence is in your strong sense, right?
Yes. Oh, yeah. That's very, strongly.
And so if you just wanted convergence of laws, that's not the point. The point is the more like the Haagerup-Thorbjornsen result about norms.
Yeah, convergence of laws already follows from Voiculescu's work.
Mm-hmm.
Yeah, because Voiculescu gives it without tensoring, but that's sort of a linear thing, right? Like the fact that it works for the tensor product is you just sort of sum things up. So there's enough algebraic structure at play that once you have it for one of the sides, in law, you don't get it for both sides. So it's really the statement about norms. And one thing maybe that I can say briefly is that it's really important that the u's and v's here are chosen independently. If I take u equals v, this strong convergence is never true. So that's sort of something subtle that happens when you go from convergence in law to strong convergence.
Do you have any other questions for Ben? Okay, then let me stop the recording.